So task 1 says that we have a dual compartment reactor separated by internal partition with equal radius. And we know that the height of the cylinder, is represented by volume over pi r squared. And that the area of each circle is pi r squared. And the surface cost is 17 ringgit per meter squared. And the internal parts, all the parts, cost 29 ringgit meter squared. Okay, so in the question, volume 1 is given as 0.06, volume 2 is given as 0.010. Thus, when we plug it into the H equation, we get this value for H1, and H2 is going to be 0.010. Same thing. So, since we want to find out the surface cost first, which depends on the lateral surface area of the cylinder, we plug in the equation times the cost. The equation for the lateral surface area of the cylinder. So we need to plug in first the H value, which we're going to add up. The total H value will give us 0.016 over pi r squared. So subbing this into the equation, first this is going to cancel out with this, which will give us over r. Okay, so now we're going to have to find the cost for each area of the circle. Now since we have 3 circles, we're going to multiply the cost by 3, which will give us 87 pi r squared. Now that we found Cp and Cs, we will have to add them up to find the total cost. So which is going to give us 0.544 r Cs plus the equation of Cp 87 pi r squared. And we differentiate it to find the absolute cheapest cost, which is going to give us minus 0.544 r to the power of minus 2 plus 174 pi r. Now we set the derivative to 0 to find our r value, and solving this to find our r value gives us this much. Now apparently this is our minimum value, but how do we know if it's a minimum or maximum? We're going to have to perform a second derivative test. So this is our second derivative equation, and when we plug in the minimum value of r, we will get this value. And we know that if it's bigger than 0, then it's a minimum value, so we just proved that this radius is the minimum radius. To find the minimum height needed, we have to plug in the r value, which is the minimum value of r that we got here, which is going to give us this value, 0.1916 for H1, and for H2, this is the value that we get. And now we calculate the minimum cost. So we also plug in the minimum r value, which is going to give us 8.173132. 32 ringgit. Okay, if the cost of all circular plates increases from 29 ringgit to 36 ringgit, while Cs stays the same, what is going to be the value of R? So we already have the stationary point equation, which is this, and if we turn it into a general equation, we get Cp times 3R and Cs plus volume 1, volume 2 divided by R squared. Okay, so we have our stationary point equation, and we want to find R. So we'll set the derivative to 0, and solve for R. And now we're going to have to generalize this equation so that we make an equation to figure out how it increases. So this is the value for if it was 29 ringgit. And if it increased to 36, we don't know what it's going to be. Therefore, so now that we generalize this equation, we will solve for R. Remember that Cs stays the same. So the only thing that changes is the Cp value. If the cost increases to 36, we will have to substitute 36 into this equation, keep Cs the same. So we know Cs is 17 ringgit. Substitute only 17 and here 36 on Cp, and we get this value. We get this value right here. And remember, at 29, this was our value. That means that the radius actually decreases to compensate for the volume staying the same when the price increases to 36. So therefore, the price will increase. When the price increases, the R value decreases if you keep everything else the same.
So next I will present that task 2, where I calculate the hydrostatic force and center of pressure acting on a reactor inception harsh using definite integrals. For explaining the calculation, I will briefly explain the concept here. So the pressure in the harsh is not constant, and it will become larger or increases as we go deep into the liquid. So pressure changes with depth, and we can use definite integral to calculate the force acting on the harsh. So to do this, let's consider a small horizontal strip its width is b, and its height is, the small portion of the height is dy. So the area is dA is equal to b dy. And the pressure acting on each strip is given as P of y is equal to P0 plus rho gy, where P0 is the gas pressure about the slurry, and rho is the density of the biomass, and g is the acceleration due to gravity, and y is the depth measured from the liquid surface. So the force acting on each strip is d of f is equal to P of y into dA, that is equal to P0 plus rho gy into B dy. By integrating the equation from top to the bottom of the hatch, we can obtain the hydrostatic force. So let's move to the calculation. We can look at the given data here. So the width of the hatch is equal to 0.60 meters, and the height of the hatch is equal to 1.20 meters, and the P0 is 2000 Newton per meter, and the density is 1015 kilogram per meter cube, and also the acceleration due to gravity is 9.81 meter per second square. So let's substitute the values in the hydrostatic force equation, where definite integral 0 to h from P0 plus rho gy into P of dy. So we can, the h is here 1.2 meters, and P0 is equal to 1000, and rho is 105 knot, and the gravity is 9.81, and where B dy is equal to 0.60 into 1.20. So we can substitute and simplify this. And from this, here we can apply the definite integral, where lower limit is 0 and upper limit. Let's continue substituting and simplifying. So after this, I'm applying the definite integral. First, as we all know, for definite integral, it is the upper limit minus the lower limit. So the upper limit here is 1.2 and the lower limit here is 0. So after simplifying the equation, we will finally get where F is equal to 5889.816 Newton. So the hydrostatic force acting on the reactor inception hatch is 5889.816 Newton here. Let's move to calculating the center of the pressure. So the center of pressure is the point where the total hydrostatic force acts on the hatch. So to find out that, we can use this equation, where YCP is equal to definite integral 0 to h y py b dy all divided by definite integral 0 to h py b dy. So we know py is equal to P0 plus rho gy, and so the denominator is the force equation that we already find out earlier, so which is equal to 5889.816 Newton. So let's continue the calculation, where YCP is equal to definite integral 0 to h from y P0 plus rho gy into B dy all divided by force. So let's consider the numerator only right now. So we can use the h is also 1.2 here. So we can substitute all the values here. So as we all know, for definite integral, the upper limit minus lower limit. So we can substitute all the values here, and finally we will get our answer 4423.85. To find out YCP, the given answer by divided by the force. So finally we will get YCP is equal to 0.7511 meter. So now we got the center of the pressure, which is equal to 0.7511 meters. So let's compare the midpoint of the hatch, and which is equal to 0.6 meter, and the center of pressure is greater than the midpoint of hatch. So the center of pressure lies below the hatch because pressure increases with depth.
Next is for our task 3. The dimensions for our dual compartment cylindrical reactor goes through repeated optimization cycles to improve accuracy. Our hydrostatic force model is also recalibrated using updated measurements. And firstly, the combined relative error in the reactor is reduced to 62% of the previous error. We also have a relative error of 6%. And the derived equation after an amount of cycles is En equals to E naught times 0.62 to the power of n. We need to find the smallest cycle number to generate a combined error below 0.5% or 0.005. After that, an updated strategy gives us a reduced error of 72% of value from the first cycle, then 68% in the second, and then 62% in the repeated cycle onwards. we need to find the smallest cycle number to generate a combined error below 0.5%. And lastly, we get 24 minutes for the first cycle, and every subsequent cycle takes 9% faster than the previous cycle. After the n amount of cycles that we found in the first part, we have to calculate the total time in minutes. Now for the solution of the first part, we are given the equation right from the task, and we are also given the maximum error percentage, which is 0.5%. Therefore, we can input the values right away to find n. Now we can input 0.005 is larger than 0.06 times 0.62 to the power of n. Now this ensures that the term n will create a number that does not exceed 0.005. We can divide both sides by 0.06 to get 0.8333 that is larger than 0.62 to the power of n. Now we can take log on both sides and use log rule to obtain minus 1.0792 larger than n log 0.62. Now log 0.62 will give us minus 0.2076. After that, we divide both sides by minus 0.2076, which will switch the sign and give us the answer that is n is larger than 5.198. Based on our answer, we would choose 6 as the smallest integer that is bigger than 5.198, and once we test it into the equation, we can see that the result is still smaller than 0.005. Therefore, our answer for the first part is n equals to 6 cycles. For the second part, we have 3 errors combined, and we have to obtain the n amount of cycles just like in part 1. Except this time, the equation model will be slightly different. Our equation will be En equals to E0 times 0.72 times 0.68 times 0.62 to the power of n minus 2. This n minus 2 means that the subsequent 0.62 is repeated an n amount of times minus the first 2 cycles.
So we determine the new minimum number of refinement cycle. The initial error is 6%, and according to the new update strategy, the error is reduced to 72% of its previous value in the first cycle, 68% in the second cycle, and 62% in every subsequent cycles. Therefore, the compiled error equation is En equals to 0.06 times 0.72 times 0.68 times 0.62 power of n minus 2. Since the required error must be less than 0.5%, which is 0.005, so we sub the values into inequality and solve for n using logarithm. After simplification, we get n greater than 5.7047. Because the number of cycles must be a whole number, so we take the minimum number of refinement cycle is 6. To verify this result, we sub n equals to 6 back into the equation. The final error is 0.00434, which is less than 0.005. Therefore, 6 refinement cycles are required. Next, we calculate the total refinement times. The first refinement cycle takes 24 minutes, and each subsequent cycle is 9% faster than the previous cycle. Therefore, the cycle time forms a geometric sequence with a common ratio of 0.91. So, we use the geometric series formula Sn equals to A times 1 minus R power of n divided 1 minus R. We sub the value inside, which is A equals to 24, R equals to 0.91, and n equals to 6. Then we obtain a total refinement time of 150 minutes 22 seconds. So the optimization process requires approximately 150 minutes and 22 seconds, or about 1 hour and 55 minutes to complete all 6 refinement cycles. So that's all from task 3. Thank you.